Okay, we need to talk about ionization energy. We need to be able to predict the ionization energies of species compared to one another and really just understand what the concept is. So, definition of ionization energy is the energy required to remove an electron from a gaseous atom or ion. Notice it does say gaseous here. So, in order to calculate the ionization energy, you have to actually get the species into the gas phase. And that's because when you're in the gas phase, and we'll talk about this more when we get into the chapter of gases, but when you get into the gas phase, the particles are assumed to not be attracted or with each other anymore. You've got them at their highest energy level, so it's easiest to deal with the atoms or ions on an individual basis. We're not dealing with an array of them coupled up together, we're dealing with an individual species. So that's why we're going to see ionization energy and in a minute, electron, different video, electron affinity, where they are in the gaseous phases. Okay. The general trend here is it increases across and it increases up the table. So when it says here, how does this relate to atomic radius? It's completely opposite. Atomic radius is the opposite trend of ionization energy. So if we look at the graph here, this graph actually tells us a lot of information about first ionization energies. Again, first means first electron removed. I can see here, this is starting, so this here is helium, or sorry, hydrogen to helium, lithium to neon, sodium to argon, potassium to krypton, rubidium to xenon. So your alkali metals, hydrogen is not an alkali metal, but of course it fits there up until your noble gases. And you can see, generally speaking, as I go up from like lithium to neon is across the table and it's increasing. Sodium to argon is increasing. Now we do see some little dips here, and we're going to talk about these individually. We need to understand what's happening here. But these dips here are very intentional, and we will talk about what how those are coming about as well. And then you can see, generally speaking, it's still kind of increasing as we go across our transition metals as well. But again, there's a little bit of dip going on, and we need to kind of understand what's going on here. So, ionization energy. Again, the energy required to remove a valence electron. It doesn't have to be valence either. I want to clarify that it could be any electron, but you remove your valence first from a gaseous atom or ion. So again, the reason it says valence here is that valence electrons are removed first, then core. So if I want to remove all the electrons, eventually I could if enough energy was provided. It is an endothermic process. Okay, I want to emphasize that energy has to go in. And I know we have not covered endo and exothermic yet, but endo means energy in, exo means energy out. So it's an endothermic process. Energy has to go in order to make the species lose the electron. You need to be able to write these reactions though. This reaction, like lithium, the first ionization energy of lithium is the removal of that first electron. So I would have lithium gas giving me lithium ion plus an electron. It's not just going to do that for fun, it's going to take energy to do so. So energy goes in to remove the electron, giving that electron as a product as well. Outer electrons are not held as tightly by the attractive force from the nucleus, again, your effective nuclear charge, or more shielded by the inner core electrons in their way to the pole of that nucleus, so they're easier to remove. And that's why I see the energy increasing as I go up the table, because as I go down the table, I'm further away from the nucleus. I apologize. I know it's really hard to read when I write like that, but it's hard for me to write at the bottom of my screen. So I'm just going to say it. As I go down the table, I'm further and further away from that nucleus. I'm further away. I'm at those other electrons. It's easier to remove them. And that's why I see the energy increasing as I go up the table, because I'm getting closer and closer to the nucleus, higher effective nuclear charge. You should know what these look like. So when I say like IE1, IE2, IEN, IE1 is the first ionization energy, the energy required to remove the first outermost electron. Second ionization energy, the energy required to remove the second electron. Third ionization energy would be IE3, energy required to remove the third. So for like lithium, the lithium gas, going to lithium plus gas plus an electron is IE1. If I had lithium plus gas going to lithium 2 plus gas phase plus an electron, that would be IE2. And if I did lithium 2 plus, giving me lithium 3 plus plus an electron, that would be all the electrons lithium has, but that would be IE3. So let's talk about these. Let's look at some numbers here, okay? When I look at these numbers, sodium versus magnesium, the first ionization energy of each one versus the second. And it's got the third on here as well. Okay, sodium, first ionization energy is 496. Second jumps up to 4560, and the third up to 6910. When I look at magnesium, I see the first ionization energy is actually higher at 738, but the second one's only 1450. So it's jumping, but not very high, and then 7730. So IE1 versus of sodium versus IE2. IE1 is 496 kilojoules per mole, whereas IE2 is 4560 kilojoules per mole. Now, some people have an easier time thinking about this when they think about the atomic orbitals. So let's go ahead and draw this out. If I'm just looking at sodium, I'm going to write, I've got 1s, 2 electrons, 2s, 2 electrons, 2p. I've got 6 electrons in 3 degenerate orbitals. I'm going to run out of space. And then I've got 3s with 1 electron. IE1 is the removal of this first electron, okay? And it's going to take energy. Yes, it's not just going to give up the electron. It's going to take energy to remove that first electron. But IE2 is the removal of this electron right here. So notice that IE2 is splitting up a full-filled shell. And I see a large increase, almost 10 times the magnitude increase going here. Now, IE3 would be this is removed, I'm removing one here. So it's not happy about it. You're into the core electrons now. So this is the core, this is the valence. It's harder to remove a core electron, so we're going to see that large jump with that difference in in the difference in energy required for that ionization energy. Now, if I look at magnesium, though, I see the first ionization energy at 738 versus the second is 1450. So it's still increasing, but it's not increasing to the same magnitude. But I want you to remember magnesium. For space issues, I'm going to not draw all of them. Magnesium has a 3s with 2 electrons in it, and then the 2p below it. So magnesium, the first electron removed is this electron right here. I need these spaced out a little bit so I can actually draw around them. So the first ionization energy is the removal of this electron right here. That's why I see it be a little bit higher than sodium, because it's a full-filled shell. It's a full-filled S shell. It's a subshell, yes, but it's a full-filled S shell. Therefore, it's got to split that up. It's going to take a little bit more energy to do so. But then when I remove that electron, if I remove that one and I'm looking at the second one, I see a bump, but not as much because it's still a valence electron I'm emptying here. So it's still just getting rid of the valence. Now, which is greater, IE1 of sodium or IE1 of magnesium, and why? Well, we see for sodium, it's 496, and magnesium is 738. And again, it comes down to sodium only has 1 electron in its valence shell, so you're just emptying that outer shell. Magnesium has a full-filled S shell. So although it's not a ton of energy, 738 kilojoules per mole isn't a ton compared to some other values here, it's still going to take more energy to break apart that full-filled S shell. And then what about the third ionization energy magnesium versus the second? Well, the third is 7730 kilojoules per mole, while the second is only 1450. And that's the same idea that we saw with sodium going from 1 to 2. Magnesium is 2 to 3. So third ionization means these two are already gone. And now I'm going after that core electron. So now it's going to be going after a core electron. It's going to take even more energy. We do have some exceptions, and I mentioned this before. Okay. So why do we have exceptions? Well, we have exceptions between groups 2 and 3 and groups 15 and 16. Between groups 2 and 3, it's easier to remove a higher energy p electron than a lower energy s. So groups 2 to 13, or sorry, yeah, 2 to 13 would be, let me look at a periodic table because I do not have that memorized. Let's see, that would be like beryllium going to boron or magnesium to aluminum. For IE1, these would be lower, these are higher. That p electron is higher energy. It's going to be easier to remove it. Plus, if I'm trying to remove from an N equals 2 group or a group 2 alkaline earth metals, they're full-filled S shell. And I'm not saying an S shell being full is the end all be all, but it's more stable than not. Between groups 15 and 16, I also see this difference, and this is because of a half-filled subshell. That's what the pictures over here are showing. So, like between groups 15 and 16, so that would be like nitrogen going to oxygen. Okay, nitrogen is part of group 15, oxygen is part of group 16. If I look at nitrogen, to remove its first electron, I have to remove this electron, giving me this. That is disrupting a half-filled shell. For oxygen, though, to remove that first electron, be removing this one, giving me a half-filled shell. So this is disruption, a half-filled shell. This is producing a half-filled shell. And don't get me wrong, oxygen wants electrons. It doesn't want you to take them away, but it's going to be easier to take them away than it will for nitrogen because of the half-filled shell. So let's go through some examples. Which is greater and why? Magnesium's first ionization energy or aluminum's first ionization energy? Magnesium is 3s1, or sorry, 3s2. Aluminum is 3p1. You can do it by electric configuration. You could do it by the trends. You could do it by atomic orbitals. I'm going to do it by atomic orbital because it makes more sense to my brain. So for magnesium, I have 3s with 2 electrons in it. For aluminum, this does have a full 3s because 3p comes after that. If you really want to draw them all out, drawing just the valence electrons out. But I've got a 3s that's full, but then I've got a 3p. Which is greater? Well, I'm trying to either remove this electron or this electron. This is easier because I'm just going to empty out the p's, which means greater is the first ionization energy of magnesium. I'm splitting up the s's. What about the first ionization energy of aluminum versus the first ionization energy of silicon? So again, 3s2, 3p1, and silicon is 3s2, 3p2. When I look at these, it's going to be greater. So looking at pulling apart the one aluminum or the one electron out of aluminum, the one out of silicon, a couple ways to think about it. One, if I empty out that aluminum, then I've got an empty 3p orbital. That's a little more advantageous. Silicon is only one spot away from gaining an electron or from having a half-filled shell. which it would like. Aluminum, if I just lose the one, I mean, if I lose silicon's electron, I still have one electron in my three P's. If I lose an aluminum, it's gone. This will be greater. This is easier to remove. That also follows the general trend. There's more electrons in silicon, which means the effective nuclear charge is greater, which means the electrons are pulled tighter. So it's also following the general trend. What about phosphorus versus silicon? Or sorry, phosphorus versus sulfur. I can read. Yeah, phosphorus versus sulfur. If I look at phosphorus, phosphorus is 3s2, 3p3, and sulfur is 3s2, 3p4. The reason I'm not doing silicon and phosphorus is because it just follows the general trend. Plus, phosphorus already has a half-filled shell. Don't take away its electron. It's not happy with you about it. Looking at phosphorus, valence electrons, I have 3 here. Versus sulfur, I have 4. So is it going to be easier to remove one electron here or this electron here? It's going to be easier to remove the electron here, which means that this is going to be greater. Again, that comes back to that exception we talked about a little bit ago with the group 15 to 16 exception. Phosphorus has a half-filled shell. It doesn't want you to take away its electron. It's got a half-filled shell. It's going to take more energy to do so. Whereas for sulfur, it doesn't not particularly want to lose its electron, but if it does, you're giving it a half-filled shell. It's going to be easier to do. What about sulfur versus chlorine? Looking at sulfur, looking at chlorine. Again, this is an energy scale over here. I always forget to write the energy part here. Sulfur is 3s2, 3p4, where chlorine is 3s2, 3p5. So is it easier to remove that one electron from sulfur than one electron from chlorine? It's easier here. Why? Well, chlorine, one, it's only one spot away from having a full filled 3p shell. It's more electronegative, which we'll talk about in a future chapter. But it's one spot away from having that full filled shell. If you take away that electron, it's still got a partially filled p. It's not half filled yet. There's no advantage to it. For sulfur, if you take away that electron, that first electron from sulfur, it's at least got a half filled shell. So it's going to be easier to remove it from sulfur. Therefore, the greater value will be the first ionization energy of chlorine. What does it mean here when it says 6 or 7, though? That means the 6th electron removed and the 7th electron removed. So let's talk about those ones. So let's see if I can get this out of here. Okay, 1, 2. Okay, so the 6th electron removed. 1, 2, 3, 4, 5, 6 versus 1, 2, 3, 4, 5, 6. For sulfur, to remove 6 electrons would empty out its energy n equals 3 energy level. For chlorine, the P's are emptied out, but it's going to split apart. So for chlorine, P's are emptied, or any 3 P's, and it splits the 3s. It's going to take more energy. It's going to take a lot of energy to do this either way, but take more energy here because I'm splitting apart that full-filled S shell. But when I look at the 7th ionization energy, this removes yet another electron. Notice for sulfur, it's already lost all of the n equals 3 electrons it has. So now we're into the 2p. Whereas for chlorine, we're removing this electron. Sulfur, I'm now trying to remove this electron. It's going to take more energy to remove the seventh electron from sulfur than chlorine, because for chlorine, all you're doing at that point is emptying out your threes. You're n equals 3 energy level. But for sulfur, you're now into the core. You're emptying out a core electron. It doesn't really want you to empty out the core. It would like you to leave it be. Okay, and our last example for this video, place the following in order of increasing first ionization energy. Lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. General trend is across the table, it increases. So I do see that these are listed in their order across the table. I do know there's an exception between beryllium and boron and nitrogen and oxygen. So group 2 to 13 and group 15 to 16. So lithium is less than boron, is less than beryllium, less than carbon, less than oxygen, less than nitrogen, less than fluorine. So general trend holds. You have to understand why it doesn't hold though, and I often do it by understanding, not just trends, because I find that the understanding behind it helps you get the right answer. The trends, you have to remember exceptions.